Yep.
I don't know if I'm mixing this up with finite,
Yeah.
but is the optimization project also like optional like group thing, or is it just individual?
Optimization is purely
Okay.
yeah. I mean, you can work together with people because, you know, I'm assuming a lot of people's widget looks similar, but everyone has to write their own report.
Okay.
Yeah.
Okay.
Mhm.
And we're getting our test back today, right?
Yes. Mhm.
We're getting back our exams soon.
Yep. Mhm.
I don't know what, I have no idea what's going on with that. I'm like,
You seem like only gonna look at our slides, I'm like, what?
I have no slides.
5 of them crowded on one computer, like, you don't have any slides.
Probably just gonna come in like, to do it. Just make a long tab. And then do that.
I don't know, I'm sure.
This week 14 or this week?
Week 15.
So what are you teaching next semester?
I have no idea.
Wait, really?
We're a little bit late this semester.
Elective wise, you don't know?
I have no idea.
Speculation.
Well, there's a grad course I'm most likely to teach just because I'm the only one who's taught that in the last 8 years.
Is that 538?
It's 540.
Oh, what's that?
It's kind of like finite elements, but for grad students.
Oh, okay.
Yeah.
Are you
Besides,
still using campus?
yeah.
Oh,
Yeah,
okay.
it's like
So
more
advanced.
advanced answers. Yeah.
Cool.
Besides that, I'm not sure. I assume I'll find out sometime before next semester, but maybe I'll just walk through the door and say, here, you're teaching this class. I'm like, oh, all right, let's go.
Who teaches that biomaterial class?
That's Dr. Sue's class. Yeah, material science is kind of her thing.
Oh, really?
Yeah.
Okay. I've never had it. Yeah.
All right, it's 4 o'clock. Let's go and get started. All right, good evening, everyone. How's everyone doing? Have a good Thanksgiving? Ready to finish up the semester? We have 2 more weeks to go. All right, so the only thing really left for this class is just the final project. So remember there's no final exam in this class. It's just the project. And so I have so at the very least we need to finish the lecture for today. I do have another set of lecture notes on just kind of general tips for optimization, just to kind of round things out. But I do want to leave next week, at the very least next Wednesday, but maybe at least maybe Monday or half of Monday or Wednesday, just to work on the project, right? So if you haven't had a chance yet to start on the project or even just kind of get started, I would definitely do that. Question.
You mean Tuesday and Thursday?
Tuesday and Thursday. I'm sorry. Yes, thank you. Yeah, so next Tuesday and Thursday, next Thursday for sure, I'm leaving it completely open just to work on the project. And then I think the next lecture notes, I'll probably get done with it probably halfway through Tuesday. And so, that's probably the best time for you to ask questions about the code, making sure you guys are set up in the right way. Now, granted, the project's not due until December 20th. But the amount of time that we have together is just kind of limited. Yeah.
Will you still be contactable after this semester?
Yes, so next week is week 16, so next week is just kind of business as usual. Finals week, I'll still be holding my office hours at normal times. If you do need to contact me outside of office hours, you can set up an appointment to do so. So just send me an email to say, oh, the office hours times don't work for me. And so, let me, can we meet at this time? And I'm pretty free during that week, so, we can meet that way.
I'm saying like after week 16, but before December.
Yes, yeah, so that's finals week. So finals week, after week 16, that week I'll be available through regular office hours. Yeah. Yep. Right. So the other thing I did over Thanksgiving was I did grade your midterm exams. The scores are already on Canvas. It might be a little bit confusing to see exactly what you got on the exam. Because if you remember, I have the policy in this class where whichever midterm you score higher on, I'm going to make that your worth 30%. And so, I already done all the swapping. And so, if you look on Canvas, say, hey, I got the same score in the second and the first exam. Well, a couple of people actually did. But, if you see that, then I swapped the two. And so, I have the exams for me today, so you can see your scores. If I didn't do the swapping properly, or, sometimes because I'm doing a manual switching, Canvas doesn't have the ability to kind of, do this, automatically. If I make a mistake in terms of entering the numbers in incorrectly, definitely let me know. But your grade should reflect, whether you did higher on the second. And I think, maybe about 70% of the class was better on the second exam compared to the first one. So I think a lot of people improve their fortune with this exam. Okay. But because of that, should both midterm scores be the same? So a couple people had the exact same scores on the on the first midterm and the second midterm. I think Jeff, I think you were one of them. So it just kind of ended up that way. But yeah, but for most people it should be different. Yeah. Mm-hmm.
What was the average?
But so because I did all the manual swapping, I didn't actually get a chance to see the average. But my general sense was the average was maybe around 38, 39 out of 50. Yeah. Mm-hmm. Okay. All right. Any questions on that? Okay. All right. So let's go ahead and get started. I'll go back to your exams after class today. I'll bring the exams again on Thursday. So if you're not here today, you can pick it up on Thursday as well. Okay, so the last topic that we're going over, we started this 2 weeks ago, actually. So, I'm going to spend a good chunk of today kind of reviewing this. It's been a while. But the last step or the last piece of information that you need to do your final project is to learn how to incorporate constraints into your nonlinear programming algorithms. Okay. So, it's been a while, so let's kind of refresh our memories a little bit. So, the entire kind of second half of the class, we've been dedicated to what we call nonlinear programming algorithms, right? So let's just kind of refresh our memories in terms of what that means. Right? So nonlinear programming is a collection of algorithms that rely just on objective function evaluations. Right? And the main thing is that we're not taking any derivatives, right? So the first half of the class, we were talking about all classical methods, so those were all derivative based algorithms. You take a derivative of the objective function, you set it equal to 0, you solve for the design variable, that's your optimum. Nonlinear programming gets around that. Okay. Because it turns out that a lot of practical situations you're going to have objective functions that you can't take the derivatives. Your final project being one of those situations. Okay. So everything that we've been going over, so coordinate search, Monte Carlo, interpolation methods, Newton-Raphson, everything that we've been going over so far has not taken into account any constraints. Okay. So constraints is a concept that we haven't seen in a very long time. But the idea with constraints is that, whenever you have an optimization problem, there are often limitations in terms of what we call admissible values for the design variables. Okay. So just some examples of some simple constraints that we've seen. So, for the most part, if you're dealing with some kind of engineering optimization, generally all of your parameters are going to be positive, right? So a lot of the variables that you're optimizing are things like lengths, things like dimensions, height, width, weight sometimes too, volume, area. So all of these quantities are positive. Right. So that's certainly true for your final project as well. So remember, your final project, you're optimizing the design of a truss structure, right? And so part of that is you're optimizing the lengths of all the different truss bars. And so since those are lengths, they must be non-negative. Okay. And of course, the operative word here is must be. Okay. Because in optimization, it sometimes can be a little bit confusing in terms of, what factors or what considerations should be constraints and what considerations should be part of the objective function, right? Whenever you're describing some kind of limitation as must be, or this has to happen, that's usually your key word for this has to be a constraint. Okay. All right. And the constraints that we usually work with in optimization, they usually take some kind of mathematical form. Okay? And the mathematical form being some kind of equation that must be satisfied based on the values of the design variables. Okay? And so what we say is that if that mathematical equation for the constraint is satisfied, whether it be an equality constraint or an inequality constraint, then we say the constraint is satisfied. Okay? So for example, if we take the constraint that we have above, that where the design variables have to be non-negative, mathematically, we can express that in the following way. Right? So we can say that x1, our design variable, must be greater than 0. Okay? Or, maybe something a bit more complex, maybe we have something like, 2x1 plus 3x2 squared has to be equal to 0. All right. So what these equations tell us is that, when we run our optimization, right, when we run our optimization, we're going to be choosing values, or we're going to be computing values of x1 and x2 that, optimize our objective function. So I don't have the objective function for these variables here, right? But the idea is that no matter what we get from our optimization, the result of the optimization must satisfy these equations. All right, so that's kind of just a basic summary of constraints. Okay, so there's also a lot of nuance here. So we have differences of inequality constraints and equality constraints depending on the type of equation that we have. In this example here, we have one inequality constraint and one equality constraint. Okay, there are a lot of tricks that you can do. So remember probably the most useful trick that we learned in the classical method is that if you have an equality constraint, you can use direct substitution, and that's still valid here. Okay. I'm bringing that up because it is possible to use direct substitution on the final project on both problems. So both on the simple truss and on the complicated truss, there is at least one equality constraint. Well, okay, there's one equality constraint on both, where you can use direct substitution to simplify your problem. So definitely keep an eye out for that. Okay. But for the vast majority of constraints, we're going to have to deal with them in a different way. Okay. The issue is that the nonlinear programming algorithms that we've developed so far, they don't have a direct way of handling constraints. Okay. And so a lot of those algorithms that we've talked about, they're kind of developed under the assumption that we can search everywhere in our domains. Okay. There are ways to kind of more directly modify those algorithms to account for the constraints. There's actually one method in the note that we're not going to go over in the class just because it's a bit too much for the last 2 weeks, called the method of feasible directions. So method of feasible directions is kind of a riff off of coordinate search and pattern search, where you make sure that whichever direction that you're searching in, you still stay within the bounds. And that's one way to do it, and that's one way to kind of guarantee that your constraints are satisfied. But there's a much simpler way that I think is a bit more practical for you guys to apply to your final projects, which is the penalty method. Okay. So that's the one I want to focus on, just because that's probably most likely the one you're going to be using on the final project. So I want to spend a good amount of time on this. Okay. Okay, so that was just kind of a recap of just constraints and nonlinear programming, just kind of getting us caught up to kind of where we are right now. Are there any questions on any of this? Okay, good. Okay. So the penalty method is nice because it's relatively simple to implement. You may not believe me when I say it's simple, but when you look at the alternative, you'll say that, yeah, penalty methods are a lot simpler. So the idea with penalty methods actually kind of goes back, it's kind of inspired in a way by our discussions on Lagrange multipliers, if you remember that back from week 4 or 5, okay? The idea behind penalty methods is to incorporate the constraints directly into the objective function as what we call penalty terms. Because we're already using an algorithm in our nonlinear programming to find the best value for this objective function. And since our constraints already have a mathematical form, why don't we incorporate it into our objective function in a way so that the algorithm kind of automatically selects points that satisfy the constraints. So we're taking our objective function, which we kind of use the objective function for a lot of things, but we're using it to enforce these constraints as well. Okay. And so let me show you the mathematical form, and then I think it'll be more clear once we kind of do an example. Okay. All right. And so the idea with penalty terms is to basically replace our objective function with what we call here an augmented objective function. So this capital F here, this is our augmented objective function. So our augmented objective function is equal to little f of x. So little f of x, this is our original objective function. Okay. So that represents kind of the original optimization problem that we were trying to solve. Okay. And then to that, we're going to add these additional terms. Okay. Okay. So we have A multiplied by summation. J is equal to 1 to M of Gj of X quantity squared plus B times summation of K is equal to 1 to P of H of X squared. Okay. Where that first term with the A, this here represents our inequality constraints. And the second term here, B, these represents our equality constraints. Okay. So basically, the idea is to take the mathematical form for the constraints. We have to kind of work on them a little bit, and then add them directly to our objective function here. Okay. So the form of this equation is actually quite interesting, and I didn't highlight this last time, but I want to bring it up here. Okay. So traditionally, like I mentioned before, like I've mentioned, weeks prior, that traditionally most optimization problems are formulated as a minimization problem. Of course, it is possible to have maximization problems, but traditionally, just because there has to be some kind of convention, just like there's the right-hand rule. There's no reason why there couldn't be a left-hand rule, but then scholars back then were right-handed, so I guess that's it, right? So maximization, minimization, it doesn't really matter. Just we chose minimization to be the standard, okay? But if you take that into account, right? And if you look at the signs of these additional terms that we've added, we've literally added them to the objective function. We can see that we're adding this A times our inequality constraints. We're adding this B term times our equality constraints, okay? Okay. So because we're adding those there, what we can say is that, if our design variables violate those constraints, it's going to make our objective function value or our augmented objective function value more positive. Okay. Notice how there are, there are there are squared terms there. So no matter what, if we violate the constraints, we're going to end up with a positive. Okay. So the G squared, we add in that value there. The A is positive. Okay. And more positive in this case means less optimal. Okay? So that's the idea with the penalty terms. These extra terms here are literally there to penalize the objective function for choosing design variables that violate the constraints. Okay. So that's why those two extra terms there, the A term and the B term, we often call those penalties. Okay. All right. So that's where we are. So the idea behind penalty terms is to not actually change the algorithm itself. So all the algorithms that you've learned up to this point, they're all perfectly valid for constraint optimization. The only change that you have to make is you have to change the objective function. Okay. All right. Any questions on this so far? Okay. All right. So let's do an example. I think it'll become a lot more clear once we do an example. Okay. Okay. So let's look at this three-dimensional optimization. So let's say we're going to minimize. We want to minimize the following function. F of x is equal to x1 squared plus 4x2 squared plus x3 squared. Okay. So three design variables here. These three design variables are going to be subject to constraints. So first constraint that we're going to levy is that each of the design variables are going to have a lower bound and an upper bound. Okay. So x1, for instance, is going to be constrained between the values of -1 and 1. X2 is going to be constrained between the values of 0 and 2. And X3 is also going to be constrained between the values of 0 and 2. Okay. So these types of constraints are very common for most, especially for engineering optimization problems. There's always going to be a lower bound and there's always going to be an upper bound for the constraints. Okay. So these types of constraints, you're going to see them in almost every optimization problem. We call these upper and lower bounds. So at the very least, knowing how to deal with these and incorporate them into your optimization is a very important skill. Okay. Now, this is not the first time we've seen upper and lower bounds. And so, we've talked about these within the context of Monte Carlo. Okay. Upper and lower bounds are a requirement for Monte Carlo just because of the randomness. And so, you have to bound the randomness. And so if you're doing a Monte Carlo method, these constraints are kind of satisfied automatically. But if you're doing another method, even random walk, and so even if you use random walk or coordinate search, pattern search, Nelder-Mead, you have to be more explicit about incorporating these into the objective functions. Okay. So you need to account for these in the objective function if you're not doing Monte Carlo. Okay. So I mentioned that there just because, I know, some of you may be interested in using Monte Carlo for your final project. Remember, you can't use pure Monte Carlo for the final project, but you can use Monte Carlo comboed with something else. Okay, that's perfectly fine. So, if you're going to do kind of a multi-step optimization, just know that for the Monte Carlo step, you may have a different objective function than the, coordinate search or pattern search or random walk step that you do. Okay. All right. So those are our inequality constraints. We also have one equality constraint here. Okay. So the equality constraint that we have is that we have x1 plus x2 squared minus 2 is equal to 0. Okay. All right, so we have well, technically 7 constraints, but each upper bound and each lower bound is considered one constraint. So we technically have 7 constraints here. Okay, so if we want to label them, so this is constraint 1, this is constraint 2, 3, 4, 5, 6, and this last equality constraint is constraint 7. Okay. So for this problem, first thing we're going to do is we're going to determine our augmented objective function. Okay. Okay. We're going to determine the augmented objective function that incorporates all of these constraints, okay, as well as the original objective function. Okay. Any questions on this before we get started? Okay. All right, so let's go ahead and get rolling. Okay, so first thing we need to do in order to incorporate the constraints into our augmented objective function is to put all of our constraints in standard form. Okay. Remember, standard form is always useful, especially in this case because we're augmenting the objective function. Even though we're adding these additional terms, the idea is that these terms are not supposed to affect the value of the objective function. So we want to essentially add 0 to it. Okay. Now, one of these constraints is already in standard form. And so if you look at the constraint number 7, that's at the top of the screen right now, that's already in standard form, right? Remember, the way to put a constraint in standard form is to make sure that 0 is on one side of the expression. Okay. And so if you look at constraint 7 up there, that one's already in standard form, so we don't need to affect that one at all. But all the upper and lower bound constraints, we do have to put them in standard form. Okay. All right. And in particular, for the inequality constraint, standard form is, with and less than or equal to some. Although it's not that big a deal for just because we're squaring them. Okay. Okay, so let's look at the inequality constraint. So let's start with constraint number 1. Okay. So constraint number 1, if we want to just list it by itself, is that -1 has to be less than or equal to x1. Okay. In other words, x1 has to be greater than or equal to -1. Okay. Okay, so to put this in standard form, right? Just to stay consistent, I'm going to kind of move everything to the left here. So we have something is less than or equal to 0. Okay. So I'm going to subtract x1 from both sides of this expression here, right? And so what we get is -1 minus x1 has to be less than or equal to 0. Okay. All right, so all I did was I moved the x1 over to the other side. Okay, constraint number 2. So I'm not going to do it for all of them just because it's they're all kind of the same, but we have x1 has to be less than or equal to 1. Okay. And so I'm gonna do the same thing. So I'm gonna take the right-hand side of this expression and subtract it through. And so we get x1 minus 1 has to be less than or equal to 0. Okay. Okay, and then you just kind of repeat that kind of over and over again. So I'm not gonna write out the full kind of math for each one, but you can see that it's all kind of the same. Okay.
For constraint 3, is it already in standard form?
Yes, that one's already in standard form. So that one you don't need to worry about. So we have 0. Well, I'll do that. So 0 less than or equal to 2, or x less than or equal to x2, excuse me. Okay. And so that one already has a 0. And so we have x2, yeah, greater than or equal to 0. So that one's already good. All right. And then constraint 4, I'm just going to list the result for this. And so constraint 4, this is x2 minus 2 is less than or equal to 0. Constraint number 5, we have x3 greater than or equal to 0. And then constraint 6, x3 minus 2 less than or equal to 0. Okay. Okay. Good. So we have all of our constraints now in standard form. Now, so I think we talked about this two weeks ago, but just to kind of refresh your memory. For all of the inequality constraints, we can't add them directly into our objective function. We have to have to perform an operation on them first.
What about number 7?
7 is already in standard form, so we don't have to kind of do anything with that. Because that one already has a 0 on that side. 7 is an equality constraint, so we'll treat this one a little bit differently as well. But we'll come back to constraint 7. Okay. So all of these are inequality constraints, and so inequality constraints, remember, are a little bit unique in that they don't reduce the dimensionality of our problem. So it's possible to basically it's possible for a range of values to satisfy these constraints, and have no effect. And so because of this, there may be situations where, maybe we're at a point where we make x2 a value of 1, right? And so our constraint in that case is x2 minus 2 is less than or equal to 0, right? So we have x2 is equal to 1, we have 1 minus 2 is equal to minus 1, okay? That is less than or equal to 0. That satisfies the constraint, but that's a non-zero value, okay? Basically, what I'm trying to say is that when we have a value of our design variables that satisfy our inequality constraints, we don't want to penalize the objective function. Okay. So let me give you kind of an example, right? So I'm just going to take one of these inequality constraints and add it into the objective function for now. So let me do constraint number 4. Let me do constraint number 4 just for this right here. Okay? So this is not the final augmented objective function. I'm just kind of showing you an example of what could happen. So this is an example within an example, I guess. So augmented objective function with constraint 4. Okay. So for example, if our augmented objective function, which is a function of 3 variables, x1, x2, x3, okay, we have to add in our original objective function. So our original objective function is x1 squared plus 4x2 squared plus x3 squared, okay? This right here, original objective function. Okay. If we were to add constraint number 4 directly into this objective function here, and we did it just kind of as it is, it would look something like this. Okay. So constraint number 4 is x2 minus 2. Okay. It's in standard form, so we can just add it in just like that, right? And we have to square it. Okay. There's another parameter out here, there's an a parameter. We'll talk more about that a bit later, but just for now, just assume that a is some constant. We can assume that it's 1 if we want it just to go away. Okay. Okay. So what we've added here, this is the standard form for constraint 4. Okay. So constraint 4, originally constraint 4 was designed so that, if it places an upper bound on the value for x2. So if x2 exceeds a value of 2, then we should penalize our objective function. Okay. So let's test a couple values for x2 that do violate this. Okay. So let's say our algorithm kind of reaches a point where it's choosing a value of x2 is equal to, I don't know, 3.5. Okay. Right. 3.5 here violates our inequality constraint. Okay. And so since the value of 3.5 for x2 violates constraint number 4, we should penalize our objective function, accordingly. Okay. So if you plug x2 is equal to 3.5, let's ignore the original objective function for now, just because we don't have value for x1, x2, right? If we plug in x2 is equal to 3.5 into here, right? We get 3.5 minus 2, which is 1.5. I don't know why I did this. 1.5 squared in my head. That's 2.25, all right? So 2.25 multiplied by a, right? And so if we do that, we plug it in, we penalize our objective function. We penalize it by a value of 2.25 times a. Again, don't worry about the value for a. A is just some positive, it's some positive number. Okay. Right. In other words, we're making our objective function more positive, right? So whatever it was before, we're adding a value of 2.25 times a, right? Which makes it less optimal. So that's good. That's exactly what we want to happen. Right? The algorithm tried to select a value that violates one of our constraints, and so we penalize it to try to bring it back. Okay, that's good. But what if we choose a value that theoretically is supposed to, be within the constraint? Okay. So instead, let's look at a value. So let's say x2 is equal to 1.5 instead. Okay. All right. So if x2 is equal to 1.5, this satisfies the constraint because our original constraint number 4 says that x2 has to be less than or equal to 2. Okay. Okay. And so since this satisfies constraint number 4, we don't want to penalize our objective function. We want to say this is a-okay, keep this is good. Okay. But let's see what happens when we actually plug this into our objective function. So if we take x2 is equal to 1.5, we plug it in up here, right? So our penalty term now is a times 1.5 minus 2 squared, right? So 1.5 minus 2 is equal to minus 0.5, right? Minus 0.5 squared, the square is going to get rid of the negative. And so we're going to end up with a positive 0.25 times a. So of course, it's less, right? But technically, this is still penalizing our objective function because it's a positive number. Okay. Which is not good, right? So we have a valid of x, we have a value for x2 here that should be perfectly valid, right? It satisfies the constraint. It also satisfies the other constraint too, because x2 here is greater than 0. But because of the form of our penalty term, we're ending up we wound up penalizing our objective function when we didn't want to. All right, so the whole point of this kind of mini example here is to show you that whenever we have inequality constraints, we have to be a little bit careful at how we form its penalty term. We can't just take the inequality constraint and just slap it into the objective function. We have to do something a little bit more careful. Okay. All right. Any questions on this? I hopefully this makes it clear about kind of why we can't do this. Okay, so how do we account for inequality constraints then? Right. And this is going to be really annoying just because we have a lot of inequality constraints here. So we have a lot to do. Okay. But the idea here is to use basically to use a function that's built into MATLAB. In fact, it's built into most programming codes, is to use what's called the maximum function. So the max function is a special function, which, first time I learned about the max function, I said, this is the dumbest function in the world because you can just look at it and see which one's maximum, right? So the way the maximum function works, right? So the function in MATLAB is literally called max, right? And so what you feed into max is you feed in two expressions, okay? Okay. So our two expressions here can be F1, F2, and max will just tell you which one is greater, which one's bigger. Which again, sounds really dumb because if it's two numbers there, you can just look at it and say like, what's bigger between 0 and 5? 5 is obviously bigger, right? But the beauty of this function is that it also you can plug in not just numbers, but you can plug in expressions as well. Okay, let me show you how to use this. And so what if instead of just plugging in our constraint directly into the objective function there, what if we use the max function instead? Okay, so if we use this for constraint number 4, what if we did 0, max between 0 and x2 minus 2? Where x2 minus 2 here, remember, this is our constraint number 4. Okay. Constraint 4 is an inequality constraint. And so what you're going to see here is that this satisfies this fixes all of our problems. Okay? And so instead of plugging in the inequality constraint directly into the penalty term, If we make our penalty term max of 0 on the inequality constraint, this will solve it. Okay. So let's see what happens. So let's redo our example here, but let's plug in our two values. So if x2 is equal to 3.5, okay, let's plug that into our max functions. We have max of 0, comma 3.5 minus 2, okay, and so that becomes max of 0 or 1.5, okay. So which one is bigger between 0 and 1.5? 1.5 is bigger, right? And so, this function will properly return, 1.5, which is our penalty. Right? So that's good. So, a value that should be penalized is appropriately being penalized with this max function. Okay. Let's plug in our other case. Okay. So if x2 is instead 1.5, we get max of 0, 1.5 minus 2, okay? And so this is max between 0 and minus 0.5, okay? I'm sorry, yeah, let me use a bigger, right away. Let's use purple. Four. And so for this one, we're looking at which one is bigger between 0 and 1.5. 1.5 bigger. And so 1.5, this is our penalty, okay? So when x2 is equal to 3.5, we're properly penalizing it by an amount of 1.5, which is good, okay? But for our second case here, if x2 is equal to 1.5, 1.5 is a perfectly valid value because it's less than 2, okay? And so we look at our max function here, we're seeing which number is bigger between 0 and negative 0.5. Bigger is just another code word for, more positive. In this case, 0 is more positive. Okay. And so by utilizing the max function here, we're able to properly kind of distinguish cases, which we should properly penalize and which cases we should not penalize. Okay. Okay. So it's going to be really annoying. So, I'm going to write out the full augmented objective function next, but it's going to be really long because we have to incorporate all these maxes for all 6 of our inequalities. Okay. It's going to be even more annoying to type it as well. So, yeah, don't be discouraged if your objective function for your final project is really long. It should be. All right. Any questions on the max function? Okay. All right. So with that in mind, let's go ahead and bring in all of our other constraints. Okay. And so we can see our final augmented objective function. Okay. So I'm going to bring in all 7 constraints now, as well as our original objective function. Okay. Okay, so our final augmented objective function, we're going to call that big F of x. This is equal to. We have our first we have our original objective function, so that's x1 squared plus 4x2 squared plus x3 squared. Okay. Don't forget your original objective function. That's very easy to forget, but don't forget it. Okay. Okay. Now we have all of our inequality constraints. And so if you look back at the original form for our penalty terms, we have this penalty parameter A, which is multiplied by all of our inequalities. Okay, we'll talk about A, that'll be the last thing we talk about today. Okay, so we have A multiplied by, now we're gonna have a lot of max terms. So, again, it's gonna be obnoxiously long, but, it's needed for this case. All right, so we have max of 0, comma, -1 minus x1, okay. Quantity squared. So, I have to kind of revise this a little bit too. So if you look at the notes that I posted online, there is a little bit of a typo here. So in the lecture notes, I put the square on the inside here. Don't write this down. I'm just showing you what it's like in the notes. So in the notes, I have a square that's kind of just on that expression there, but that's actually incorrect. And so in order for this to work properly, you need the square to be on the outside of this expression. Okay. So just kind of make sure you do that. Okay. And so this right here, remember, this is our constraint number 1, okay, that we talked about above. Okay. Now we're going to do this 5 more times, okay, and then we have our equality constraint after that. Okay, next we have constraint 2. So constraint 2 is max. A question in the chat. So can I explain again how we determine what is penalty and what is not penalty? Like what made 0, 1.5 penalty and 0, -2, 0.5 not? Yeah, good question. So that kind of goes back to kind of how this constraint originally was. Okay. And so if you look at constraint number 4, so constraint number 4 is the one I'm looking at, is this one right here. So constraint number 4 basically specifies that our value for x2 has to be less than or equal to 2. Okay, let me bring it out here. Right, that was the original form of the constraint before we put it in standard form. And so, when I was doing this kind of mini example here, or this example within an example, I was kind of giving you 2 cases where, a case where we got a value for x2 that violated this constraint, and another case where we got a value for x2 that satisfied this constraint. And so when x2 is equal to 3.5, right, if we think back to the original constraint here, right, 3.5 is going to violate this constraint because 3.5 is not less than 2, right? And so when we plug that into our penalty term here, right, so x2 is equal to 3.5, this violates our constraint. Okay. So since x2 is equal to 3.5, since that violates the constraint, we want to penalize our objective function, right? And so through this max term here, we're going to add a value of 1.5 squared times a to our objective function, so that penalizes it, right? So when I say penalize, a penalty basically just makes our objective function more positive, right? And so by adding a value of 1.5, right, that makes our objective function more positive. Because if it doesn't violate the constraints, then we just kind of leave it alone, and so we just kind of let the original objective function kind of take over. And so for the second example here, when we had a value of 1.5, so this satisfies our original constraint. And so original constraint, at least for the one that we're considering for just this part here, which was x2 is less than or equal to 2, right? 1.5 is less than or equal to 2, so that does satisfy it. And so in this case, we don't want to penalize the objective function. And so by using the max function, we can see here we have this comparison of 0 and minus 0.5, okay? The max function will select the value here that's more positive, which is 0, okay? Right? And if we're adding 0 to our objective function, then we're not penalizing it at all. And so, we're saying that this value of x2 is good, And so, it passes the test and then we can kind of move on from there. Okay, so that's why I kind of say here that there's no penalty. Does that make a bit more sense? Okay, good. Okay, so let's continue on. So let's go ahead and write out the rest of the penalty terms here. So let's go to constraint number 2. So constraint 2, we have max between 0 and x1 minus 1, okay, quantity squared. And this here is the term for constraint number 2. Okay. Okay. Now we have constraint 3. And actually, I think I misspoke earlier too. So for constraint 3, I basically said that this is kind of the standard form here. But in order for this to work, and because we're using the max function, we actually need to invert this, which is kind of annoying. So we basically need to say that minus x2 is less than or equal to 0. And then for constraint 5, you have to say that minus x3 is less than or equal to 0. So, it looks like it makes no difference, but, when you're using the max function, it actually does make a difference. So, so when we incorporate constraint 3, we're taking the max between 0 and minus x2, quantity squared. So this here is constraint 3. Then we have constraint 4. Constraint 4 we've already seen. So this is max between 0 and x2 minus 2, quantity squared. This is constraint number 4. 2 more of these. I told you it gets really obnoxiously long. Okay. We have max between 0 and minus x3, quantity squared. This is constraint number 5. It's not all going to fit on one screen. So we have max of 0. This is constraint number 6. Constraint number 6 is x3 minus 2, quantity squared. Constraint 6. Okay, so those are all the inequality constraints for this problem. Okay. We do have one equality constraint, so that's constraint 7. So the nice thing about equality constraints is that you don't have to do anything fancy. You don't have to do any max function. You can just add the equality constraint directly into the objective function. Okay. And so for the equality constraint, let me see. We have b times quantity x1 plus x2 squared minus 2 quantity squared. And this one right here is constraint number 7. Okay. All right. So that right there is our augmented objective function for this problem. So it's grown quite a lot. And so, our original objective function looked pretty modest. And so our original objective function was only x1 squared plus 4x2 squared plus x3 squared. Okay. But because of all these constraints, we have to add in all of these terms here. Okay. Which again is normal, right? So, this is not unusual. So, for your project, if you have a lot of constraints like this, don't worry, that's what it's supposed to look like. This is kind of the cost of the penalty terms. All right, any questions on this? Okay, so there is an example code that incorporates this. In fact, it uses the Nelder-Mead algorithm. Oh, questions?
Called an augmented function.
Yeah. Yeah, so this is the this big F here, this is the augmented objective function. So there is a code that incorporates this, and so if you do want to see it in code, I believe it's called, let me see. So the example code is called C underscore NLP underscore example. I believe it's example 2. Okay. I have it posted on Canvas for week 15, but if you wanted to see it done, that's where it is. Okay. And so this basically utilizes Nelder-Mead. So we didn't talk about the algorithm at all here. We just talked about the objective function. But this code here utilizes the Nelder-Mead algorithm with this augmented objective function. So it's also good to look at, just because I know we didn't, I didn't test you guys on Nelder-Mead, so no, probably not a lot of people looked at it, but it's a good one to use for the final project. So I would definitely take a look. Okay, so the last thought that I want to end on today. So a little bit of this is going to spill over to Thursday, so we'll pick this up on Thursday as well. But I wanted to talk a bit about these A and B variables, right? Right, so we have this A variable here and this B variable here, right? So what the heck are these things, and what do we even do with them? Okay. So the purpose of those parameters there are to help you enforce the constraints. So let's give them a name first. So A and B are what are known as the penalty parameters. Okay. And their purpose is to basically control how strictly your algorithm is going to, enforce the constraints. Because I'm going to tell you a secret about, well, it's not really a secret. I don't know why I said that. That was really weird. But, I'm going to tell you something about the penalty method. Is that they actually don't guarantee that you're going to satisfy the constraints by the end of the algorithm. That's probably the biggest weakness of penalty method terms. And so they are quite simple to use. You don't have to modify your algorithm at all. And so if you already have something that works for unconstrained case, which most people do, you don't have to make any changes to that algorithm. You just add to the objective function. Okay. The big weakness is that, there's no guarantee that you're going to actually satisfy all the constraints in the right? So of course, you're going to penalize all the values that don't satisfy the constraints. But just like in real life, you can penalize someone all you want, but sometimes they're still going to break the rules, right? And so you can still I think of my cat. So I always get upset when my cat jumps up on the counter and steals my food. I can spray it with water all I want. It's still going to jump up and do it. So optimization algorithms are kind of the same way. Okay. And so what we usually say is that a penalty method is not a strict enforcement of the constraints, it's a soft enforcement of the constraints. Okay. Now, how do we make this a little bit more strict? Well, we can modify those penalty parameters. Okay. In a nutshell, if you increase the value of the penalty parameter, so you increase it from a value from 1 to 10, that's going to make the enforcement more strict. Basically, you could think of that as if you increase the value of the penalty parameter, it's going to make the penalties for breaking the constraints more severe. Okay. And so if you do that, of course, the algorithm is going to be more encouraged to satisfy the constraints by the, okay. So then, if that's the case, why don't we just use, values of 1,000,000 for these penalty parameters, right? If our goal is to satisfy all the constraints in the end, why don't we just make this as strict as possible? Well, of course, there's a caveat to it. And so if you make the penalty parameters too large, then you don't want that to overtake your original objective function. Okay, so there's a delicate kind of balance to play here. And in fact, there's actually a strategy to actually make sure that you end up with something that is optimal and satisfies the constraints. But we'll go over that next time. Okay. Any questions on this before we wrap it up for today? Okay, all right, so for those of you in class A, I do have your exams, so you can come forward and pick those up. Put those on this desk here. If you're coming on Thursday, I'll bring the exams again then, so you can pick up your exams then. But if not, thank you guys for coming today. We'll wrap up this lecture next time, and then we'll start kind of wrapping up the class. So thank you guys for coming. I hope you guys have a good rest of your day, and I will see you on Thursday.
Oh,
Hey,
I was curious, why don't we just use direct sub instead of the penalty methods for the equality?
that is actually the preferred.
Okay,
And so if you have an equality constraint where you can direct sub, that's
that's what I was
that's
thinking,
easier.
because I was like, that would make it a lot shorter.
Yeah. But sometimes you also get equality constraints that don't have the objective or they don't have the design variables directly in them. So you may get a situation. So there's no such case in the final project, but you may get a situation where you have an equality constraint based on a derived method. And
I
so-
like, instead of the force needing to be less than, you could have the force needs to be less.
Exactly. Yeah. So that would be a case that will incorporate into the objective.
Into this form.
Yeah. But if you have a form which you do direct stuff, that's always.
Okay, that. So like some of the ones we have there, like the basic ones, we can just use the direct sub that the height is related to the line.
Exactly.
Oh,
I found your 441. I don't know if you saw that.
I saw that.
Yeah. So they just, I think either I might have marked it incorrectly and say I would pick it up or it got lost.
Okay, cool.
Yeah, they had it, I picked it up, graded it. So.
I'll be able to pick it up tomorrow.
Yeah, okay.
Thanks.
Mhm. Yeah. Sure.
So on canvas, it's setting out at 35.
Remember I swapped scores.
So that's what happened. Was-
Yeah, so if you get, so I think you did better on this one, so I swapped, because the way I set it on Canvas, the midterm 1 is worth 30% of the grade,
Okay.
midterm 2 is worth 20%.
Okay,
So since you
I
did
thought
better,
it was, that makes sense. I thought it was like you would replace the first one and the sub-assembly score on the second.
Oh, no, so I mean, you still keep both same scores, just whichever one gets higher, and that's worth a higher percentage. So because you got 35 on the first exam, then I put I moved the 35 to the second.
The other one?
Yeah.
Okay. So just curious.
Yeah.
So what, like, did I do wrong on this one?
So this one, so I'm asking for patterns, pattern searches. So coordinate searches, you step in the X direction, you step in the Y direction. Pattern search, you actually need to take a step.
That's what I kind of like wrote, like, this is the pattern direction, like, that's the new, like, way that we're moving now.
Yeah, but then I still want to see the arrow.
I thought that's what that was that I was drawing,
So
because,
that's the pattern, but then we actually need to take a step. That's why I only took out one.
all right, then, yeah, I guess, thanks.
Yeah.